Let's talk about the conclusion. What is the conclusion of all we have heard so far about solving an equation, finding the roots of functions? All the methods we talked about bisection, we talked about Newton, we talked about the secant method, and we talked about the regular Falsi method. All of them had one thing in common, and this is the user must provide suitable initial values, and only if these initial values are provided in an appropriate way which fits to the situation, only then the methods are capable of finding the zeros. This is the situation for all of these algorithms. Especially in situations where the function, for example, has more than one zero, so maybe 2 or 3 or 5 or 6, the user must set an initial value 3 times to find all 3 zeros. But if the user does not know how many solutions there are, how could he set 3 times appropriate initial values? So the situation is a very bad one. If you have a function, you are looking for the root. Maybe there are several roots, but only one of them is the one you are really looking for. Then maybe with an initial value not appropriate to the solution you want to find, you will find a nonsense solution which you are not looking for. So this is a bad situation. If you have this situation, if you want to find this root, you have to know that it's more or less in this interval, and then you can find this root. And if you on top want to find that root, you have to specify this interval and you have to specify this interval. But sometimes it's a very long straight line, and so this is not an easy task. So this is our situation, and worse than the left hand side example is the right hand side. We also talked about in the last video. This is a very bad situation, very oscillating, heavily oscillating function, and then somewhere there are 2 roots. But how can you know that this is the starting interval? You are looking for solutions in that interval. How can you know that? Okay, so that's the situation, and not only for the algorithms we talked about, but also for professional MATLAB or professional Python, this is the same. You only find a zero if you start near it. This is very unsatisfying, and unfortunately there is no remedy. Not for our algorithms, not for the algorithms used by MATLAB or by Python. Imagine you are searching for a treasure which is worth $20 million, and you know there is one in a square with side length 100 kilometers. And someone tells you that there's a specific device, in our case the algorithms we talked about, which help you doing that task. Then maybe you heard that they are very effectively in finding the roots or in finding the treasure. You are very excited and you say, okay, I will use that device and buy it. And when using it, you realize that the device only detects the treasure if you set appropriate starting values which are close to the thing you are looking for. And let's exaggerate that situation and say, let's say, you need a deviation of at most 5 meters to find the treasure. So this device is worth a little. It's worth a lot. If you are close in the range of 5 meters, then it will tell you, although it's hidden under the ground maybe, but you need to find the treasure in a range of 5 meters, and in a square of 100 kilometers you have no chance. It's unsatisfying. So for specific classes of functions, especially for polynomials, there are algorithms which will find all the solutions and will never miss one. Okay, but when the basis is some evaluable function and you pass the name of that function to MATLAB and tell MATLAB, please evaluate that function, and by doing so please find the root, then MATLAB has no chance to do some logic to surely find all the roots. MATLAB tells you, please give me initial starting values, otherwise I cannot start, or I can try, but if I'm not successful, I will tell you that I need better initial values. That's the truth about MATLAB and Python, and about all the others as well. Never forget that truth. Unfortunately, this truth is not considered plausible, and typically one assumes that not me being the user has to provide initial values, but the intelligent algorithm will find. And maybe you spend a lot of time modeling and you are very glad to find the equation, and then you will be a little astonished when you find out that F0 does not, as you assume, that you on top need a good approximation of the solution you are looking for. For me, this also happened. Sometimes I was perplexed. I had the situation I wanted to find best fit parameters. Some of you know what I mean, some of you don't. It doesn't matter, and then you have an equation, and then you can take the derivative, and then you have to find a solution of the system of equations we see in the next chapter. And then I assumed, okay, having done all that stuff, now MATLAB will find the solution, but it did not. And this is unsatisfying and very surprising. Please never forget that truth.